Sklearn random projection. Description: random projection is a dimensionality reduction technique that projects high-dimensional data onto a lower-dimensional space. It is based on the idea that high-dimensional data can often be represented in a lower-dimensional space without losing too much information. Random projection is a fast and efficient technique that can be used for a variety of tasks, such as data compression, feature extraction, and outlier detection. Inputs: X. The input data, which is a 2D array of shape n samples. N features. Each row represents a data point, and each column represents a feature. N components: the number of dimensions to project the data onto. This should be an integer less than or equal to the number of features in the input data. Outputs: X new the projected data, which is a 2D array of shape n samples. N components. Each row represents a data point, and each column represents a dimension. Transformer: the random projection object that was used to perform the projection. Steps: a random matrix is generated with a specified size, typically based on the number of features and the desired number of components. The input data is then multiplied by this random matrix to project the data onto a lower dimensional space. The resulting data is the projected data, which has a reduced number of dimensions. Metrics: explained variance measures the amount of variance in the original data that is preserved in the projected data. Reconstruction error measures how well the original data can be reconstructed from the projected data. Time complexity measures the computational time required to perform the projection. Visualization plots: scatter plot of the projected data in 2D or 3D. To visualize the structure of the data in the lower dimensional space. Pairwise scatter plots of the projected data. To examine the relationships between the different dimensions. Fine-tune parameters: n components: the number of dimensions to project the data onto. Apes: the desired accuracy of the projection. This parameter controls the trade-off between accuracy and computational efficiency. Random state: the seed for the random number generator. Uncertainty methods: confidence intervals for the projected data can be calculated using bootstrapping or other resampling methods. The uncertainty of the projection can be assessed by comparing the reconstruction error of different random projections. Challenges and fixes. Challenge 1: choosing the right number of components. Sample use case that resulted in challenge 1: if too few components are chosen. Information may be lost if too many components are chosen. The dimensionality reduction may not be effective. Fixes to challenge 1: use cross-validation or other model selection techniques to determine the optimal number of components. Challenge 2: dealing with noisy data. Sample use case that resulted in challenge 2: noisy data can lead to inaccurate projections. Fixes to challenge 2: pre-process the data to remove noise before performing random projection.